In this lesson, we will be looking at equilibrium constant. Equilibrium constant is represented by a capital K. In this unit, equilibrium constant can be represented as either KEQ, meaning equilibrium constant, or Kc, meaning concentration constant. These two can be used interchangeably. For any system at equilibrium, there is a mathematical relationship between the reactant and product concentrations. This mathematical representation can be expressed as the ratio of the product concentration or concentrations over the reactant concentration or concentrations. For the general equation AP plus BQ in equilibrium with CR plus DS, A, B, C, and D are the coefficients that are used to balance the equation. P, Q, R, and S are the reactants and the products. Therefore, the equilibrium expression can be represented as the concentrations of the products divided by the concentration of the reactants raised to the power of their coefficients. Kc, as noted, is sometimes used instead of KEQ when units are of molar concentration. However, the units of K depend on the particular reaction. That is, it is different for each reaction, and therefore we will be omitting the units on K only for this unit. The value of K, meaning the size or magnitude, depends on the temperature and only the temperature. That means K is constant at a constant temperature. Therefore, the only thing that can change the answer for K would be a change in temperature. A change in concentration or pressure will just mean that the equilibrium will shift to maintain the same ratio. As well, solids or liquids are not included in your K expression. The reason that solids or liquids are not included in our K expression is because their concentration is constant, and we only plug in concentrations into an equilibrium expression. Given the rules that we've learned until now, we're now going to practice writing out an equilibrium constant expression for these three systems that are at equilibrium. The first thing that you should do when looking at an equilibrium is to skim the equilibrium for liquids or solids. Remember that liquids and solids are not included in the expression, so I'm going to put an X through those so we'll remember not to use them. Also remember that the K expression is a ratio of the products to the reactants, so we're going to use products first. Our product in this expression is H2, and it has a coefficient of 3. So we're going to say H2 cubed. We're also going to use square brackets because square brackets indicates concentration. Over the concentration of water, H2O cubed. Let's look at the next expression. Very quickly skim through to see if there's any solids or liquids. You'll notice that carbon is a solid here, so we will omit that for the K expression. Therefore, K is equal to H2. This has a coefficient of 1, but we do not need to put in the number 1. It's assumed all over H2O. The last equilibrium, you'll notice, has water liquid, which is not included. So here, our K expression, our product is CH3, COO, C2H5, all over C2H5OH times CH3COOH. We're soon going to get to some mathematical examples. Before we get there, however, there are some rules that we need to be aware of. First, in terms of interpreting K, if you get an answer that is smaller than the number 1, you would say that the reactants are favored. If you get an answer that says K is larger than 1, you would say that the products are favored. So in the event that you're asked to make a statement about the position of the equilibrium, you would have to look at your answer for K and from there determine if reactants or products are favored. In the event that you are given K forward or K reverse, you can always find the other one by finding the inverse of the other. For a given system at equilibrium, the value or the magnitude of the equilibrium constant depends only on the temperature. So recall from earlier that the only way to change the actual value of K is to change the temperature. Why is this? Because changing the temperature of a reacting mixture changes the rate of the forward and the reverse reactions by different amounts. The reason for this is because the forward and reverse reactions have different activation energies. Let us now look at some calculations involving the equilibrium constant. There are 3 different types of K calculations in this chapter. Given the equilibrium concentrations, find the value of K. Find a missing concentration given the value of K and the other concentrations. And 3, given initial concentrations and equilibrium data, find K. In this lesson, we will be looking at types 1 and types 2. On a public exam situation, these 2 would be multiple choice questions. Example number 1. Calculate the value of K if 0.0045 moles per liter of trinitrogen hexoxide and 0.0300 moles per liter nitrogen dioxide were found to be the concentration of the gas at equilibrium. The first thing we would need to do is scan our equilibrium to see if there's any solids or liquids. Gases and aqueous solutions are included in our K expression, and we'll have to write out that K expression for this equilibrium. KEQ is equal to the product, NO2, raised to the power of its coefficient, 3, over the reactant, N3O6. We can now plug in the equilibrium concentrations. We were told that nitrogen dioxide had a concentration of 0.0300 cubed. We're also told that trinitrogen hexoxide had a concentration of 0.0045. Since we are not including units for the K expression, we can omit moles per liter in our workings. We now have to plug this in our calculator and give an answer to the appropriate number of significant figures. 0.0300 has 3 significant figures. 0.0045 has 2 significant figures, so our answer should also have 2 significant figures. So the answer here is 0.0060. Example number 2. The equilibrium concentrations of hydrogen and iodine are both 0.0122 moles per liter. Calculate the molar concentration of hydrogen iodide in this system at 700 Kelvin. The first thing we need to do here is write out our equilibrium expression. Quickly skimming the equilibrium, there are no solids or liquids. So KEQ is equal to the product, HI, raised to the power of its coefficient, which is 2, over H2 times I2. We can now plug in what we know. We were told that K here is equal to 54.6. We're looking for HI squared, and we know that H2 and I2 are both 0.0122. You can write that as 0.0122 times 0.0122 or as 0.0122 squared. To get HI by itself, we must now cross multiply. HI squared is therefore equal to 54.6 times 0.0122 squared, which comes out to be 0.00813. Then to get HI by itself, since right now it's being squared, we take the square root of both sides so that HI by itself will equal a concentration of 0.0902 moles per liter or molar. Since we're solving for concentration here, we must remember to include our units. Additionally, the original number 0.0122 as well as 54.6 both have 3 significant figures, so my answer will also have 3 significant figures as well. I strongly encourage that you practice both example 1 and example 2 by completing the worksheet that follows.